Okay, let's talk about inverses. So inverses are extremely important in certain types of mathematics, right? They allow us to answer questions that otherwise are very, very difficult to answer, especially if you want to turn around the question and ask it from a different perspective. So what we have here is an example of an inverse function. Essentially, what an inverse function does is it undoes the original function. So if I have a function that adds 50 to something, then the inverse function would subtract 50. It would just undo whatever the original function was doing. So if we have a function that multiplies by 2, then the inverse function is going to divide by 2, right? So it just puts it back in its original state. So if we think about that on an individual basis, we think about that by the points that are on a function, then it should look something like this. This is just a simplified example. But see how we have the function f, and it turns 1s into 2s, 3s into 4s, and 5s into 6s? Well, this is our f inverse, and we use this notation of f with a -1 superscript. That is not an exponent. That does not mean f raised to the -1. That is a different thing algebraically. This is just the notation we use to signify the inverse of the function f. Well, what f inverse is going to do is undo all the steps that were over here. So it needs to look like this. If f turns 1s into 2s, then f inverse better turn 2s back into 1s. If f turns 3s into 4s, then f inverse better turn 4s back into 3s. And if f turns 5s into 6s, f inverse has to turn 6s into 5s. So it's essentially just swapping the x's and y's, right? And we'll see that that actually gives us some symmetry geometrically in a minute when we look at the graph. So we can fundamentally just think of inverses. They're just undoing what some other function does, and you literally can just reverse the ordered pairs that are members of that function in order to do that. Now, that's a little harder to do when we're not dealing with ordered pairs directly, but let's start off in the simplified case. So if we think about our composition that we did earlier, if we send something through, if we compose a function and its inverse, then we should get back what we started with, right? So if I take 3 and send it through f, I get 4. And then I send the 4 through f inverse, I'm back to 3. So we compose these two functions and they completely undid each other. That's how you actually know if two functions are inverses or not. We can approximately tell if two functions are inverses by looking at the graph, but that's not 100% accurate. It's pretty darn good and works most of the time. But if you really need to prove that something is an inverse, you prove that when you compose them, you compose those functions, and you should end up with x, which is generally the thing you started with. Okay. So what does that look like from a graphical perspective? So keep in mind, as we look at the graph, we're taking the xy pairs and we're just switching them. That's what we do with an inverse. So we can see that here. Let's take the function y equals x squared. Well, what happens if I switch the x's and y's? Well, what happens is we end up with a reflection across this line y equals x. And you can see that right here. When we reflect that, we get this. So our upright parabola x squared became a sideways parabola. But this is what you get when you reverse all the x's and y's on the blue curve. You get these ones on the green curve. So you can see there's a symmetry there. Your brain can kind of look at this red line and go, yeah, okay, I can kind of see what's going on here with this green one. Well, like watch if I change this a little bit, and your brain's going to immediately go, something's wrong. So watch when I do this. +1. Oh, that doesn't look right anymore. That doesn't look like it's a reflection, like it's a symmetry. It looks like something's off. But as soon as I put it back, we go, oh yeah, I can see how reflecting this blue across the red line gives us the green. So let's go back to our vertical line test. So remember how that works. I'm passing a vertical line over my parabola, and it's only ever hitting the parabola at one point, telling us that this quadratic, this parabola, is in fact a function. Okay. Well, think about what happens to a vertical line when we reflect it across the line y equals x. It becomes a horizontal line, right? Right here. So if we take this horizontal line here and we see that, well, if we had a thing called the horizontal line test, which we will in just a minute, it looks like this fails it because the horizontal line hits our graph 2 points at one time. Well, what happens when we reflect that horizontal line? We get a vertical line. And that vertical line will test if our inverse is a function. In other words, This thing right here, the green graph that we come up with, that fails the vertical line test. Okay, because we can see it hitting 2 points here, meaning the green graph is not a function. Okay, well, we can tell that ahead of time because this vertical line translates to a horizontal line when we transform it, and our original function fails the horizontal line test. So if your original function fails the horizontal line test, that tells you that when you find the inverse, it's not going to be a function because it's going to fail the vertical line test. So it's just kind of a shortcut to, you don't have to go through the step of finding the inverse and then testing if it's a function. We can just run the horizontal line test on this quadratic. It fails, so it passes the vertical line test and is a function. It fails the horizontal line test, which tells us that when we find the inverse of this, it will fail to be a function. Okay, so that's what the vertical line test tells you if a graph is a function. The horizontal line test tells you if it has a functional inverse. Okay, so just kind of keep those two straight. And then this symmetry that we're seeing is really helpful if you want to check. Just put your graph in there, put its inverse in there, what you think is its inverse, and see if that symmetry holds up. So what can we do with this situation where we want to find an inverse for a quadratic, but we're not able to do that? Well, instead of using the whole parabola, maybe we're doing a problem where we don't care about negative values. Maybe it's a time problem, and negative time doesn't make sense in our problem. So instead of dealing with that whole parabola, why don't we just cut it in half and use the half that we care about right here? And then when we reflect that, now we get this, and now the inverse is a function. Right? So now we can find the values that we want. So that's how things should look graphically. So the two takeaways graphically is that when you have a function and its inverse, you get this symmetry with respect to the line y equals x. And then also the horizontal line test will tell you if a function even has an inverse. All right, so how do we deal with a function when it's in this function notation, right? It was fairly easy when we were dealing with tables. All we had to do was take the x's and y's and switch them. And then we saw some convenient patterns when we were looking at the graph that there is a symmetry, so we can kind of visually inspect if we're doing the right thing or not. But what do we do in a case like this where we have the functional notation? How are we going to go about this? Well, effectively, we do the same thing that we did before where we swap the x's and y's, except now we're going to be doing it with our variables, whereas before we were doing it with specific numbers. Okay, but this is powerful. This allows us to switch all the x's and y's at the same time. So for finding an inverse algebraically, there's 4 steps, and 3 of them are super easy. And then step number 3 ranges from being sometimes easy to sometimes impossible. Okay, so we'll just have to kind of see how that goes. So step 1 is that we're going to take our function notation, and we're going to replace it with just the variable y. Remember, f of x is equal to y. F of x represents the output from a function, and so does y. They represent the output from the function. So we can use them interchangeably. But for this particular problem, it's easier to deal with an equation than it is to deal with function notation. So that's why basically all step 1 does is converts it to an equation that is easier for us to deal with. Okay, the next step, step number 2, is we're going to switch all the x's and y's. So that's kind of what we looked at earlier where we were swapping the x's and y's in our table. Now we're doing it with our variables, and it's switching all of our x's and y's. So you can see that y equals 2x minus 1 over x plus 3. This is the same thing, but just with our x's and y's switched. So x equals 2y minus 1 over y plus 3. And then now step 3, this is the one that ranges from easy to hard to sometimes impossible to do if no inverse exists. We want to solve for y. So we need to solve for a variable. I see 2 immediate issues that we need to remedy. The first is that there's 2 y's. I'm supposed to solve for y, but there's 2 of them. And the second is that one of those y's is in the denominator. So we have to fix both of those problems if we're going to try to go through and solve for y. We're going to go through and we're going to multiply both sides of this equation by y plus 3. That gets the y that's in the denominator out of the denominator and makes it a little bit easier for us to deal with. So all I've done here is I've multiplied both sides of the equation by y. And now what we're going to do is We want to collect our y terms on one side of the equation, and we want anything that is not a y term on the other side of the equation. So you can see that's what we're multiplying out here. I'm distributing the x in to get xy plus 3x equals 2y minus 1. And now we're going to collect those y terms so that they're on the left, and the non-y terms are going to be on the right. Right? And so we do that by adding and subtracting our terms from both sides of the equation. So we end up with xy minus 2y on the left, right? I've subtracted 2y from both sides. And we end up with negative 3x minus 1. I've subtracted 3x from both sides, and we end up with this line right here. Now what we do when we have our y terms together, I'm going to factor this y out. And that takes care of our second issue of having two y's. Now look at that. Once we factor the y out, we're down to just one y. Right? So that's great. We have y times x minus 2 equals negative 3x minus 1. So basically, these parentheses is just some junk multiplying our y. Well, if we have junk multiplying our y, then we should divide that junk out. And that's basically what our last step is we're dividing both sides by x minus 2, and we end up with y equals negative 3x minus 1 divided by x minus 2. And our last step here is another easy step. We did the hard part already. Step 3 is the hard part. Step 4 is easy. We just turn that y into f inverse. So remember, step 1 was to turn f of x into y. Our last step is to turn y into f inverse of x.